Hi, everyone. I will do my best to talk into the microphone, and if I fail to do so, please let me know. So welcome to the beginning of your theory boot camp in 4 hours. I'm going to give you just a really brief overview of what the hands-on tutorial is going to be, and then let you all sort of run loose and play with the Colab notebook. I think Dawn wanted all questions to sort of be directed into Slack, but we also are here to answer your questions in the flesh. So I'm here to answer questions. Sarah Moran, who's sitting up here in front, is also here to answer questions. Wow. I thought we only had 2 helpers. This is incredible. Okay. Awesome. Well, we have so many people in the audience just ready to answer your questions. So I encourage you to talk to the helpers. Also talk to your neighbors just about what you're finding and what you're doing. I will say now, and I will say again, these notebooks are designed to run theoretically. In a perfect world, you could hit run all and all the cells would run and you would complete the exercise. That doesn't necessarily mean that you will have learned a whole lot in doing so. And so throughout these exercises, it's super important that you sort of run the cells, really explore the models, and this will really enable you to take these same skills and apply them to other planets, which is really the goal of these hands-on sessions. So we're going to be working today with PICASO to do forward modeling. PICASO is not even close to the only forward model that exists to do this kind of spectroscopic modeling. But the principles that you learn and sort of the components of modeling are really similar across a bunch of these different codes. And so if you take what you learn here in terms of the components of modeling and decide you really hate PICASO, I encourage you to look into other codes and sort of explore what works best for you. Though today you're going to be focused on modeling transit spectroscopy of gas giants, PICASO has capability to model other things, other planets and other types of geometries. So everything from brown dwarfs, although that says young planets, directly imaged planets, terrestrial planets, and also planets in reflected light at different phases. And swapping between these different methods of computing spectra is really easy within the code. So again, even if you really hate transit spectroscopy, learning how to use and go through the framework that you're learning today will enable you to do all sorts of other different types of modeling, other different types of facilities, everything from JWST Hubble, and also sort of next gen facilities, and even sort of high resolution ground-based spectra as well. If you get stuck today, I would of course, ask people in the room if there are other components of the tool that you're interested in using. I highly recommend you go to the Read the Docs page that has a ton of different tutorials based on different things that you might be interested in doing. The way that our tutorials are structured is they start out with the basics of each different type of spectroscopy, from reflected light, transmission, and thermal emission, which includes sort of brown dwarf modeling. Am I doing something wrong? Oh, okay, cool. Oh, gotcha. And then we go into sort of a deeper explanation of cloud modeling with Virga, which you all will touch on today. And then actually teach you how to do 3-dimensional modeling. So today we're only going to talk about atmospheres in 1 dimension, but PICASO does handle things like 3-dimensional thermal emission and phase curves. So if that's something you're interested too, I encourage you to check that out. Climate modeling we'll cover today, and then the group project is really focused on fitting models to data. And so there are tons more resources here, including other bonus things like best practices for how to store your models to make sure that your model results are reproducible, and also just general code help. The other awesome resource that we have is auto generation of BibTeX references, so that when you're using our model, you can easily sort of transfer your results to papers and know sort of what you need to put within what you need to cite within your publications. The other thing, if you're interested more in the derivations of the code, so what's happening behind the scenes, there is a separate website that takes you through sort of the derivation of PICASO. You learned about some of these fundamentals of radiative transfer from Paul earlier, but this tutorial really tries to connect the derivations of the code with the model itself. And so it takes you through sort of the derivation of the radiative transfer equation. And when you get to a point where there is an equation that is actually used in the code, we hyperlink to the GitHub so you can sort of check out the derivations and follow the code in sync so you can sort of understand what is going on. We also have visualizations to sort of teach you if you want to learn more about what these different parameters in the code are. So all in all, there are tons more resources to help you learn. And today, in the next sort of 1 hour, we're really only going to be scratching the surface. So theoretical modeling in general is comprised of 5 main modules. And of course, there's many others. These are the ones that we're going to be focusing today. The opacities that serve as the initial sort of baseline input data that go into computing models, the chemical models that Julia Moses talked about earlier today, climate modeling, cloud modeling, which you'll hear about, I think, more tomorrow, and then the final generation of the spectra. So the notebook starts with opening up what we call in PICASO the open action, which establishes a connection between the model and where your opacities are. Now, opacities are basically give you critical information about how different molecules absorb light, which of course we need to model full spectra of planets, spectra of anything. These cross sections are computed line by line at really high resolutions, R of a million. But it ends up being a really huge data set. So more than about 16 gigs or more per individual molecule. And so in order for you to model a planet, it would be completely impossible for me to provide you with all of the data necessary to do this modeling. And so what we do in order to make modeling feasible, or one method that we use to make this modeling feasible, is to resample the cross sections onto a smaller grid. And so the file that was included within your Sagan Summer School notebook was this resampled grid with only just a few molecules to sort of get you started. But if you're really interested in pairing your models to higher fidelity data, especially at higher resolution, it's really important for you to think about what cross-section file you've downloaded. And if you go to the PICASO documentation, there are different sorts of opacity files available on Zenodo for you to download, depending on what you're interested in modeling, depending on what resolution your data exists at. And you'll also notice, so when you're resampling cross sections, you have to rebin your final spectra to about 100 times lower. And so you'll notice throughout this tutorial that you're constantly using this mean regrid method to bin your data down to about an R of 100, which is what the WAS39 data is sampled at. So the next component is the chemistry, which we're using chemical equilibrium models. You'll notice this nice Chemek-Vischer function, which is based on Shannon-Vischer's chemical equilibrium grid. Within the notebook, you'll see, at first glance, these functions are very simple. They require as input 2 parameters. I think you all have talked a lot about C to O and metallicity maybe throughout the week, and I'm sure we'll hear about it more. But I encourage you to sort of read through the documentation and understand, really try and build an intuition for, sorry, this is cut off, but this axis here is C to O. So, and this axis is the abundance of these different molecules. And so as you input these different values for parameters like C to O and metallicity, really try and consult these sort of references and understand, given a certain input of C to O and metallicity, are you getting out what you expect? Are you operating in an atmosphere that is potentially water dominated if you're at low C to O, and or dominated by carbon species if you input a higher C to O value? So make sure you explore the output again as you're going through the motions. The next piece is the climate modeling, which will likely be maybe the piece that gives you the most grief. Climate modeling also often causes a lot of headaches because you have to try and converge your models. This piece starts with providing an input guess to your model. And so here you can see if we start out with a simple guess that is an isothermal profile, based on the upper boundary conditions that are set by the stellar irradiation, lower boundary conditions that are set by the internal temperature, your model is going to try and converge to a steady state solution and give you out the appropriate or the corresponding chemistry. And so you'll go through these motions to try and compute these climate profiles. And once you have a climate profile, you can use that as input to create a cloud profile. So in a perfect world, all of these things would be iterative, right? Your climate depends on what chemistry is in your atmosphere. Your cloud profiles depend on what your pressure temperature profile is. For the simple exercise, we're going to just do this all sort of in sequence order. So you're going to compute chemistry, you're going to compute the climate, and you're going to take that climate and compute the cloud. So there's no feedback. There's no feedback between the clouds that you produce and the climate model and the eventual climate model. But we are actually currently working on putting in those capabilities within Virga. And if you're interested, please come talk to me. So Virga is the second cloud, the second model that's sort of embedded within this tutorial. Virga gives you out 3 specific parameters that you need to do your spectra. The optical depth, which basically describes how much cloud is in your atmosphere. The asymmetry parameter, which we usually refer to as G, which describes how forward or isotropic the particles in your atmosphere are. And then lastly, omega, which is the single scattering albedo, which describes how much scattering your particles are exhibiting or how absorptive your clouds are. So these 3 parameters ultimately go into computing your spectrum. And then the final part is computing the spectrum, which is probably the easiest part. But the problem is, oftentimes, once you compute your spectrum and you go through all of your chemical modeling and your cloud modeling, your models often never match the data that you were given. And so you're often left wondering why that is and what you need to do to improve your model. And so that is really the foundation for the workshop that you all will be doing today. The idea is you're going to start out very simple with simple like isothermal pressure profiles, simple chemical models without clouds, and sort of start to improve the fidelity of your model by increasing the complexity until you're able to match the WAS39 initially released data set. And so this is an example of the very first attempt at doing the modeling in the notebook. And so you'll notice that there are these embedded group discussions throughout the exercise. And the idea is for you to talk to your neighbors and really think about this. So, what part of this model did you get right? What part of it did you get wrong? What assumptions did you make when you created this that could be affecting your fit to the data? And how might you move forward and improving that? Of course, the notebook is set for you. So if you just scroll down a little bit more, you can probably see the answer of what could be improved. But I really encourage you all to really have these discussions with each other so that you can try and go through this process by yourself, because in real life, you won't have a nice guided notebook to tell you what to do next. And then you'll sort of, here's another example of, we've increased the fidelity a little bit, but we still have these different kinds of models that some maybe don't match the data and some maybe do. And so you can start to think about, what model values could we potentially reliably estimate based on this simple forward modeling example, or what additional complexity could improve the fit. So in general, your goals for today and the next, I have no concept of time, 2 hours, whatever, minus I've been talking, is to, one, at the very base level, just understand what modules, what inputs are needed to create model of a spectrum. If that's the only thing you learn, I think that's awesome. 2, determine how to really dissect a planetary spectrum. This means not just creating the spectrum, but understanding what you're looking at, what molecules are absorbing, or what molecules are actually creating the absorption features that I'm looking at. By understanding those resources, when your data doesn't match your model, you can try and use your intuition to point yourself into the right direction. And then lastly, to understand just how to increase the complexity of your model. It's often not the case that you have to start off with the most complex model, and often the case we never do that, right? You start with the least complexity in your model when you're trying to compare a model to an observation, and then you statistically try and increase the complexity of your model to understand, you know, what data driven, you know, what is your data driving? What complexity does the data really want? And so we're going to do this by hand. And I just want to briefly say how this connects to the following session, Paul's session on the retrievals right after this. This is cut off, but this is a figure from Ryan McDonald's Poseidon code, which is another great open source model for doing forward models and retrievals. But so the forward model piece is really part of every retrieval scheme, right? Embedded in any retrieval code is a forward model. The piece that is usually different between codes is the radiative convective climate model, which oftentimes is too slow to run within a retrieval framework. So you can see in this sort of schematic here that at the top in the little image of the PT profile, you're often using parameterizations of pressure temperature profiles instead of actually radiative convective models. And so that's one major piece that's going to be different between this and the next hands-on session. And in this hands-on session, you're really going to be doing this parameter estimation kind of by eye, just going through the motions of trying to fit the data by toggling with different model outputs and modules. And then in the group project, and well, in Paul's session, then you're going to be doing that robustly and really trying to figure out, when you let parameter estimation operate on its own, how are you able to make inferences about the data? And then for the group project, you're going to be using grid models to do a more robust chi-squared analysis of a large grid of forward models. And I think that is all I have. Just some final tips. Like I said, just resist the urge to just click run on all the cells. Really make sure that you're exploring the code and understanding all of these different pieces. Talk to your neighbors, ask lots of questions. There's the Python help channel in Slack if you have specific coding questions, but we can also help field some of those as well. And then lastly, make sure that you try and debrief these group discussions with a neighbor as you go through the exercise. And I think with that, I will let you all run wild. Does anyone have any questions before we start? Wow. Wonderful. We'll see how long that lasts.